Take an ordinary pane of glass, the kind you'd find in a window, and shine a beam of light straight at it. What happens? Most of the light passes through, of course, but a small fraction turns around and comes back. Roughly 4%. Out of every 100 photons that hit the surface, about 4 reverse direction. That raises an immediate question. How does a photon choose? You send 100 identical photons, all striking the same glass at the same angle. 96 go through. 4 reflect. Why those 4? What makes them different? You might guess the glass has tiny flaws, little patches that reflect and little gaps that let light pass. That sounds reasonable, but it's wrong. You can polish glass until it is nearly perfect down to the atomic scale, and you still get the same 4% reflection. The photons aren't bouncing off defects. So maybe the photons themselves vary, as if each one has an internal mechanism that decides whether it will pass or bounce. That idea sounds strange, but it isn't completely absurd. Except there's an experiment that wipes it out entirely. Take an extremely thin sheet of glass, a film, so now you have 2 surfaces instead of 1, a front face and a back face. If each surface reflected 4% independently, you'd expect around 8% total reflection. 4 from the front, 4 from the back. Simple addition. But that is not what happens. Not even remotely. Depending on the exact thickness of that film, the reflection can be anywhere from 0% to 16%. 0, 16. The same material, the same light, just a different thickness, and the reflection swings from nothing at all to 4 times what you'd expect. How can that be? How can adding another surface sometimes erase the reflection from the first one? It's as if the back surface is somehow reaching forward in time and telling the front surface not to reflect. And if you keep increasing the thickness, the pattern repeats again and again with perfect regularity. With precise instruments, you can watch this cycle continue for millions of repetitions. Millions. This is not a tiny effect. It's a core feature of how light behaves. So what is actually happening? This is where things get genuinely unsettling. The only explanation that matches every experiment is that light does not choose a single route. It doesn't decide whether to reflect or transmit. Instead, and yes, this sounds insane, light takes every possible path at the same time. When a photon reaches the glass, it does not pick. It explores all options simultaneously. It reflects off the front surface and passes through. It reflects off the back surface and passes through. It does all of it at once. Every possibility happens together. So then why do we see definite outcomes? Why does the detector either click or stay silent? Here's the crucial point. Each possible path carries something called a probability amplitude. You can picture it as a tiny arrow. These arrows have directions. When you add them, arrows pointing the same way reinforce each other. Arrows pointing in opposite directions cancel. So when light hits a thin layer of glass, the arrow from the front surface reflection and the arrow from the back surface reflection might line up. Add them, and you get a large arrow. That means a high chance of reflection, 16% instead of 8%. But if the thickness is slightly different, those arrows may point in opposite directions. They cancel perfectly. The result is 0 reflection. The contributions from the front and back literally wipe each other out. And this is not just about glass. This is everything. Mirrors, lenses, rainbows, the blue of the sky, why metals gleam, why water is clear. All of it comes down to these tiny arrows either adding together or canceling out. All of it depends on light exploring every possible path at once. The theory that describes this is the most accurate theory ever built. Its predictions are correct to 12 decimal places. If you used it to measure the distance from Los Angeles to New York, it could give you the answer within the width of a human hair. That's how precise it is. And yet, if you ask a physicist why light behaves this way, why it takes all paths, why probability works through these arrows, you won't get an answer. Not because no one has tried. Generations of brilliant minds have tried. The honest response is, we don't know. Nature simply behaves this way. Think about a mirror. You probably learned that light reflects according to a simple rule. The angle in equals the angle out. That's true, but why? You were likely told that light travels in straight lines and bounces like a ball. In reality, light reflects off every part of the mirror. Not just the center where the angles match. Every point, even the edges, even the corners. The light reflecting from the far edge of your mirror is real. It exists. It happens. So why do we only see the reflection from the middle? Because of the arrows again. The paths from the center of the mirror all take nearly the same time to reach your eye. Their arrows point in similar directions, so they add up, they reinforce. But the paths from the edges take very different times. Their arrows spin around and point all over the place. One edge contributes an arrow pointing one way. The next spot contributes one pointing the opposite way. They cancel. The edge contributions disappear. You can actually demonstrate that the edges do reflect. If you take a mirror and carefully remove parts of it in a precise pattern, blocking only the regions that would produce canceling arrows, the edges suddenly start reflecting strongly at angles that should be impossible. That is exactly how a diffraction grating works. It's just a mirror with most of it cleverly blocked so cancellation can't occur. Light doesn't know the law of reflection. It doesn't know that angle in should equal angle out. It goes everywhere. The simple rule is an illusion created by interference. The same logic explains refraction. Light doesn't bend in water because it knows to slow down and change direction. It takes all paths through the water. The paths where it bends the wrong way cancel. The paths where it bends just right are the ones whose arrows line up. Every simple rule you learned about light in school emerges from something far deeper and far stranger. Light tries everything, and the rules appear from interference. This was one of the great discoveries of 20th century physics. And honestly, it has never felt intuitive to anyone. You can calculate with it perfectly. You can build lasers, fiber optics, and modern technology on it. But truly understanding why nature works this way remains elusive. So far, we've only talked about light bouncing. But light does more than bounce. It interacts with matter, with electrons. And this is where it becomes even more bizarre. Here is what we know for certain. In the entire universe, when it comes to light and matter, only two kinds of particles are involved. Just two. Photons, which are particles of light, and electrons, which are the particles that make atoms function. That's it. Two actors. Every color you see, every reflection, every shadow, the fact that vision exists at all, comes from these two particles performing a simple dance. There are only three things that can happen. Three basic actions. A photon can move from one place to another, an electron can move from one place to another, and an electron can emit or absorb a photon. That's the full list. Everything else is just different combinations of these three actions. Think about a red apple. Sunlight photons strike electrons in the apple's surface. Those electrons absorb the photons, shift around, and emit new photons. Because of the molecule structure, red photons are emitted more than blue ones. Those red photons travel to your eye, hit electrons in your retina, get absorbed, and trigger signals that your brain interprets as red. Every step is just those three actions repeating. Photon moves, electron moves. Electron exchanges, photon. Over and over. Now comes the strange part. Each of those actions has a number attached to it. A probability amplitude. One of those little arrows. For a photon traveling from point A to point B, there is an arrow. For an electron moving from A to B, there is an arrow. And for an interaction, an electron emitting or absorbing a photon, there is also an arrow. That interaction arrow is always the same size. Always, no matter what. It's a single number, about 0.1. Square it and you get about 1%. 1 in 100. This number is one of the deepest mysteries in physics. It appears everywhere. It sets the strength of the electromagnetic force. It determines how atoms bind. It defines the scale of chemistry. And no one knows where it comes from. You can measure it with incredible precision. It is approximately 1 over 137, about 0.0073. Physicists call it the fine structure constant. Ask why it has that value instead of another, and you get silence. Shrugs, speculation, no answer. It's like asking why light has its speed or why the electron has its mass. These are numbers we can measure but cannot explain. They are brute facts about reality. So we have three actions and their arrows. To predict what happens in any light-matter interaction, you do something remarkable. You draw diagrams. Not just any sketches, but specific ones. You draw every possible way the event could unfold using only those three actions. A photon travels, hits an electron, the electron moves, emits another photon. That photon goes somewhere else. Every sequence. Then you calculate the arrow for each diagram by multiplying all the arrows in that sequence. Photon moves, multiply by its arrow. Electron moves, multiply by its arrow. Interaction, multiply by 0.1. After you have all the diagrams and all their arrows, you add them. Some reinforce, some cancel. The final arrow you get is squared, and that gives you the probability. Every interaction introduces another factor of 0.1. One interaction gives 0.1, 2 gives 0.01, 3 gives 0.01. The more complex the diagram, the smaller its contribution. This is why predictions are possible at all. The simplest paths dominate. The complicated ones fade away. You can ignore most of the infinite possibilities because their arrows are too tiny to matter. But not all of them. And that's where the precision comes from. To get extremely accurate results, you must include more and more of these small corrections. When you add thousands of them, the predictions match experiments to 12 decimal places. No other theory in science comes close. Now here's something that sounds impossible but is required. In these diagrams, photons can do things that should be forbidden. They can move backward in time. They can exceed the speed of light. They can have negative energy. How is that allowed? The answer is that these photons are never directly observed. They are called virtual photons. They exist only inside the calculation. A real electron emits a virtual photon. That photon does something impossible. Another electron absorbs it. The final result is just two electrons repelling each other. You never see the virtual photon. You can't detect it. It exists only as a mathematical step. And here's the strange part. You must include these impossible paths. If you only include the sensible-looking ones, the predictions are wrong. The theory works only when you allow these absurd intermediate steps. The rules seem crazy, but they give exactly the right answers. This is what physicists mean when they say nature is absurd. Not random, precisely absurd. Which brings us to the haunting question. Why these rules? Why this interaction strength? Why do arrows add this way? Why? Does probability come from squaring the amplitude? No one knows. These questions have been asked for nearly a century. The brightest minds have struggled with them. We are no closer to answers. The theory works. It works spectacularly. But understanding why it works is still beyond us. There is honesty in admitting that science is not about pretending to know everything. It is about being exact about what we do know and clear about what we don't. We know how light behaves. We can calculate it with extreme accuracy. Why it behaves that way remains a mystery. Maybe someday someone will uncover the reason. Maybe the answer is hidden in an equation that hasn't been written yet. Or maybe some things simply are what they are. Until then, we keep calculating. We keep testing. We push the precision higher, looking for any crack in the theory. So far, there are none. Just this strange, beautiful picture of light exploring every path at once, and mathematics always landing on the correct answer. When you step back and look at it, it's unsettling. We began with a simple question: how does light work? And the answer is that it does everything at once. It doesn't choose. It doesn't decide. Interference selects what we observe. Then we went deeper and found that all interactions reduce to three actions. Photon moves, electron moves, electron exchanges photon, and these combine through arrows that add and cancel to produce the world we see. When you truly absorb this, something disturbing becomes clear. The solid world of definite events and straight lines is not the fundamental layer. It emerges from something far stranger beneath. Beneath, there are no single paths. There are all paths. There are no definite outcomes until measurement. There are only superimposed possibilities. The classical world is what remains after countless cancellations. This is not a temporary gap in our understanding. As far as we can tell, there is no deeper clockwork. The quantum layer is the bottom. Arrows, interference, probability. That is what reality is. People searched for hidden variables, for a deterministic script underneath. They looked for decades. Nature does not hide information. The randomness is real. Probability is fundamental. This was difficult to accept. Some of the greatest physicists spent their lives trying to avoid it. They failed. Not because they lacked intelligence, but because there seems to be no escape. This is simply how the universe works. Physics gave up the dream of perfect prediction. Even with complete knowledge, the best you can do is calculate probabilities. That is the ceiling. And oddly, the theory that accepts this limit is the most accurate theory ever created. Nature does not share our discomfort. Science does not exist to make us feel satisfied. It exists to describe reality as precisely as possible. Once you accept this, the weirdness becomes beautiful. Light exploring all paths is not just bizarre, it is elegant. All of chemistry and biology emerging from three actions is profound. The fact that we can predict anything at all in a universe this strange is astonishing. This understanding did not come from philosophy. It came from experiments. Nature forced it on us. We did not choose quantum mechanics. The evidence left no alternative. That is how science works. You follow the data, even when it leads somewhere uncomfortable. We now have a theory that explains every optical phenomenon ever observed. Every color, every reflection, every rainbow, every laser. But we do not know why the theory is true. We do not know where the rules come from. We do not know if they could have been different. Maybe we are still learning. Maybe there is another layer. Maybe there always will be. 100 years ago, we didn't even know light came in particles. Now we predict its behavior to 12 decimal places. We build technologies that would have looked like magic. The universe is stranger than anyone imagined. And somehow, against all odds, we are beginning to understand it.